All right, today we're going to talk about a mathematical hero. I'm not kidding. This thing swooped in and saved engineers from this world of complex, wavy chaos. Its name is the phasor. And it's this incredibly elegant shortcut that, believe it or not, literally powers our modern world. So here's how we're going to break this down. First, we'll look at the big challenge, the problem that needed solving. Then we'll meet our hero, the phasor, and its, let's call it a sidekick, impedance. We'll see how they work together, and then we'll wrap up with why this old-school trick is still so important today.
Okay, so first things first, let's set the scene. You know the electricity in your house, the stuff coming out of the wall? Well, it's not a steady stream. It's what we call alternating current, or AC. And that means it's constantly wiggling back and forth in this really smooth, continuous wave.
And mathematically, that wave looks like this. Now, I know, an equation pops up and it can look a little intimidating, but stick with me, it's actually pretty simple. It's just describing three things about the wave. That V0, that's just the amplitude, how tall the wave is. Omega is the frequency, you know, how fast it's wiggling. And that last symbol, phi, that's the phase. It's basically just where the wave starts.
So you'd think this would be a simple question, right? What happens when you run this wave through a circuit? You'd think so, but for the longest time, the answer was a total headache. For engineers, it was this recurring nightmare. A nightmare of, you guessed it, calculus.
Yeah, this quote from an old engineering textbook really says it all. It highlights the massive roadblock they were up against. Imagine, every single time you wanted to analyze a circuit with an AC source, you had to start from scratch, wrestling with the same messy math over and over again.
And yikes, this is what that messy math looked like. To get a single answer, you had to solve these gnarly differential equations, and you had to do it for two different parts. There's this initial chaotic part called the transient response that kind of fizzles out, and then the part that actually matters, the steady state wave that just keeps on going. And they had to do this for every single calculation. This right here, this complexity, is the villain of our story. So yeah, they desperately needed a shortcut. And thankfully, they found one. It was this brilliant concept that came about in the late 1890s, and it was called the phasor. So what is a phasor transform? Well, think of it like this. Imagine you're looking at a spinning Ferris wheel. Instead of trying to describe its motion constantly over time, it's up, now it's over here, now it's down, you just take a snapshot. You capture its size and its position in one single moment. That's what a phasor does for a wave. It represents the entire wave with a single static arrow, kind of like a vector. And that little arrow holds the two most important things: its amplitude, which is the length of the arrow, and its phase, which is just the angle it's pointing.
Okay, now here's where the real magic happens. The key that makes this whole transformation possible is something called Euler's identity. And honestly, it's one of the most beautiful equations in all of math. It's the bridge. It shows us that these exponential functions, which are super easy to handle with algebra, are secretly made of sines and cosines, you know, the things that are a total pain in calculus. This right here, this is the magic spell. It's what lets us jump from that wavy, complicated time domain into the much simpler world of complex numbers.
And look at this. This shows you the result of that magic spell perfectly. On the left, you've got the whole messy, time-varying wave with all its wiggles. And on the right, it's phasor. Just a single, clean number that captures the amplitude A and the phase angle phi. Boom. All that wavy complexity, gone. Just squished down into one elegant little term.
Okay, so that's great for the signal itself. We've got our shortcut. But what about the stuff in the circuit? You know, the resistors, capacitors, and inductors. How do they act in this new phasor world? Well, it turns out they get their own special translation too.
And that brings us to a new concept called impedance. We use the letter Z for it. You can think of it as, like, resistance plus. See, regular old resistance just opposes current. But impedance, it opposes the current and it takes care of the weird phase shifts that capacitors and inductors create. And the best part? A version of Ohm's law still works. The phasor voltage is just the impedance times the phasor current. Simple.
So check this out. Here's how it all translates. A resistor, super simple. Its impedance is just its resistance, R. No drama, no phase shifts. But inductors and capacitors, they're different. Their opposition to the current actually depends on the frequency, that omega. And you see that little imaginary number J? That's not just some weird math thing. That J is the secret sauce. It represents the 90-degree phase shift these parts create. In a way, that J is where all that nasty calculus went to hide. All right, We have all the pieces now. We have a way to simplify our signals, and we have a new language for our components. So you know what that means? We can finally go back to that original, messy problem, and we're going to solve it the easy way.
That whole complicated mess we saw before, it boils down to just 3 simple steps. 1, you transform the problem out of the time domain and into the phasor domain. 2, you solve it, but with basic algebra, not calculus. And 3, you just transform the answer back. Calculus, yeah, it's completely out of the picture. We kicked it out.
Okay, let's put it to the test with a real textbook example. Now remember, in the old world, the hard way, finding the current in this circuit meant we'd have to roll up our sleeves and get ready to solve a nasty differential equation. But now, we just do step 1, transform. And look how clean this gets. The voltage source, that's now a simple phasor. The resistor's impedance is just its resistance. And the inductor and capacitor, they turn into simple impedance numbers based on their values in the frequency. That's it.
Now for step 2, solve. And since all these parts are in series, we can just add their impedances up. I mean, think about that. No derivatives, no integrals, just addition. Then we pull out our new Ohm's law. The current is just the voltage divided by the total impedance. This is just some arithmetic with complex numbers. Your calculator can do this in like a second.
And just like that, a quick calculation gives us the answer for the current in phasor form, of course. So what this is telling us is that the current's wave will have an amplitude of 2 amps, and it's going to be shifted a little bit by about negative 23 degrees compared to the voltage. Simple as that.
And finally, step 3. We just translate that phasor back into the time domain. And there you have it. That is the final steady-state answer for the current in that circuit. No differential equations, no worrying about transients, just a clean, simple, and frankly beautiful process.
Now, I know this might seem like just some clever math trick for solving homework problems, but the reality is, this shortcut is one of the absolute pillars of modern electrical engineering. It's not just a trick, it's fundamental.
I mean, really think about it. The massive power grids that light up our cities, the Wi-Fi and 5G signals bouncing all around us right now, even the filters inside your stereo system that shape the sound, all of them are designed and analyzed using phasors. It's the tool that lets engineers wrangle the unbelievable complexity of countless sine waves interacting with each other.
Just like this quote says, this simple procedure didn't just make an engineer's job easier. You could argue it made modern electronics possible. It's what gave us the tools to build the incredibly complex, interconnected world we live in. Without this shortcut, progress would have been so much slower.
So the big takeaway here isn't just about circuits. It's about how a single, powerful, simplifying idea can completely reshape an entire field of science. The phasor took this world that was ruled by difficult calculus and blew it wide open, making it accessible with just simple algebra. It's a lesson that's just as true today as it was back then. You know? Sometimes the biggest breakthroughs don't come from more brute force, but from finding a more elegant way to look at the problem.